Let's take a journey back to the early 1900s. Electronics were in their infancy, massive devices filled with a maze of tangled wires. Every connection was handmade, circuits were prone to failure, and innovation felt slow and clunky. Fast forward to the 1940s during World War II, when the demand for compact and reliable electronics grew exponentially. That's when an idea sparked a revolution. In 1943, Paul Eisler introduced the concept of printed circuits, a breakthrough that changed everything. By the 1950s, PCBs were transforming technology, replacing endless wires with something sleek, efficient, and reliable. Thanks to this innovation, we now have powerful computers, sleek smartphones, and the advanced gadgets we rely on every day. It's all thanks to the printed circuit board. Picture this, a bustling city with streets winding through neighborhoods connecting homes, shops, and offices. Each road plays its part in keeping the city alive and running smoothly. Now imagine if these streets were replaced with a chaotic mess of paths that tangled and overlapped. It would be impossible to navigate, right? That's where a printed circuit board, or PCB, comes in. Think of a PCB as the city planner for electricity. It's a flat, organized board that keeps all the parts of an electronic device in place and connected. Resistors, capacitors, microchips, they're like the buildings in our city, and the PCB's thin, flat lines, called traces, act as the roads. These traces guide electricity to every part of the circuit, ensuring everything works together in harmony. Without PCBs, electronics would be like that messy, tangled city impossible to manage. Instead, they allow devices like your phone, TV, and even your car to run smoothly and efficiently. Next time you pick up a gadget, remember, inside there's a little city of components, all connected by the quiet brilliance of a PCB. Imagine you're holding a PCB in your hand. It might look like just a piece of plastic with some metallic lines and colorful markings, but beneath the surface lies an intricate structure that powers the electronic devices we use every day. Let's peel back the layers to uncover the secrets of what makes a PCB so extraordinary. At the very core of every PCB is its base material, also known as the substrate. Picture a sturdy foundation for a house. The base material, often made of fiberglass, provides strength and rigidity. It ensures the board can withstand heat, stress, and time. This is where it all begins. Next comes the copper layer, the lifeblood of the PCB. Imagine tiny highways carved into this copper, creating pathways for electrical signals to travel. The front copper layer handles connections on the top, while the back copper layer serves the bottom. For complex circuits, additional internal copper layers form a dense network, just like multi-level roads in a bustling city. Covering the copper is a layer of vibrant color, the solder mask. Often green, but sometimes blue, red, or even black, this layer acts as a protective shield. It prevents accidental contact, avoids short circuits, and protects the copper from oxidation. Without this layer, the delicate highways of copper would be vulnerable to the elements. Look closer, and you'll see labels, symbols, and tiny text on the surface. This is the silkscreen layer, the map of the PCB. It tells us where components go, what each part does, and makes assembling and troubleshooting the board a breeze. Think of it as the user manual, printed right onto the board. Finally, the edge cut defines the board's shape and size. It's like a tailor cutting fabric to fit a design. This layer determines where the PCB ends, where slots or mounting holes are placed, and how it fits into its final destination. For more advanced designs, there are additional layers that add precision and functionality. Imagine layers that act like invisible hands during assembly, or layers that ensure components fit perfectly together. Let's explore a few of these extraordinary layers. These layers hold surface-mounted components in place during assembly. It's like glue that ensures nothing shifts during the soldering process. Defining where solder paste should go, These layers are crucial for creating precise stencils that guide the placement of components. These layers ensure there's enough space around components, avoiding overlaps and making assembly smooth and error-free. These include fabrication-specific details, dimensions, outlines, and notes that guide manufacturers in crafting the board. These layers track changes made during the design process, acting like a record of revisions for engineers and designers. These custom layers allow designers to add personal notes, mechanical guides, or extra details for unique projects. With these layers uncovered, you can now see how every piece comes together to create a robust and functional PCB. Each layer plays a critical role in bringing a PCB to life, making it the backbone of modern electronics. Now that we've explored the layers of a PCB, let's dive into the fascinating variety of PCBs that power our world. As we go through each type, watch closely to see how they differ and how each one plays a unique role in electronics. Let's start with the simplest, single-layer PCBs. These boards have just one layer of copper, making them straightforward and reliable. You'll often find them in basic devices like calculators, toys, and remote controls. Simple but essential. Next, we have double-layer PCBs. With copper on both sides, these boards allow for more complex circuits. They're perfect for devices like audio amplifiers and power supplies, where performance demands more connections. Then come the game changers, multi-layer PCBs. Imagine multiple layers of copper stacked together, creating dense, interconnected pathways. These boards are the backbone of high-tech gadgets like smartphones, computers, and advanced medical devices. They make cutting-edge technology possible. For designs that need to bend and move, we have flexible PCBs. These are made from materials that can twist and turn, making them ideal for foldable gadgets, wearable devices, and other compact designs where space is limited. Next is the hybrid solution, rigid flex PCBs. These combine the stability of rigid boards with the adaptability of flexible ones. You'll find them in cameras, aerospace systems, and medical devices places where durability and flexibility need to work hand in hand. For applications that deal with heat, there's metal core PCBs. These are built to dissipate heat efficiently, making them perfect for high-power uses like LED lighting and automotive electronics. And finally, there's the perf board, also known as the dotted PCB. This simple and customizable board features a grid of dots and holes, making it a favorite among hobbyists and beginners. It's perfect for testing and prototyping circuit designs before committing to a full PCB layout. Each type of PCB has its role, addressing the unique demands of modern electronics. From simple gadgets to advanced technology, these boards bring innovation to life. Now that we've uncovered what PCBs are and the many forms they take, let's pull back the curtain on how these circuit boards come to life. It all begins with a vision and a blank digital canvas. Step 1. Designing the PCB. Engineers sit down with specialized software like KiCad, Altium, or Eagle to draft every trace, every layer. Copper paths, silkscreen labels, solder mask zones, even the precise edges of the board are all carefully mapped out. For advanced boards, extra layers like paste and courtyard zones guide how components will be mounted later. This isn't just drawing, it's engineering at a microscopic level. Step 2. Printing the design. That digital blueprint is now printed, not on paper, but onto a copper-coated board. In multi-layer designs, copper sheets are stacked with insulating layers in between, like a circuit sandwich. Specialized printers handle this with sub-millimeter precision. Step 3. Etching the copper. Once the layout is printed onto the board, it's time to carve out the actual circuit. The board is placed into a special chemical solution, usually ferric chloride or ammonium persulfate, that begins dissolving all the unwanted copper. But the parts protected by a photoresist layer remain untouched. Slowly, the copper pathways begin to emerge, like tiny highways etched with invisible hands. This is where the circuit takes its physical form, delicate traces that must be perfect in width and spacing, or the board won't function. For multi-layer PCBs, this process is done for each layer separately, then all layers are precisely aligned before being fused together. Step 4. Drilling the holes. With the copper traces now defined, it's time to make way for the components. Precision drills punch tiny holes into the board, some thinner than a strand of hair. These holes will hold components or connect different layers of the PCB. In multilayer boards, they're called vias, channels that let signals travel between layers. Once drilled, these holes are plated with copper to form seamless electrical connections from one side of the board to the other. Step 5. Solder mask application. Next, a protective layer is added, the solder mask. It shields the copper from oxidation and short circuits. It's also what gives PCBs their iconic green, blue, or black color. Step 6. Silkscreen printing. Time for identification. Symbols, component labels, pin numbers, all printed in white or yellow. It's like giving the board its own language so that engineers can read and build it with ease. Step 7. Component assembly. And now, the magic happens. Resistors, capacitors, microchips, all come together. Some boards are hand-assembled, others are built at high speed by robotic arms using surface mount technology or through-hole technology. Paste layers guide exactly where the solder should go. Precision at its finest. And just like that, a plain copper board transforms into the brain of a device, ready to bring your phone, your watch, your world to life, all through a process that starts with design and ends in precision. Every connection has a purpose. Every trace is deliberate. But a board is only a stage. The real story begins with what is placed on it. Components, small in size but full of potential. Some resist, some store, some decide. Together they don't just power devices. They shape what happens next. What gives them that power? The answer is not just electrical. It goes deeper. This is just the beginning. What comes next is what we are here to uncover.